Hello everyone, welcome to my channel. Today we will see chemistry class 12 chapter 1, that is solid state. Now see students, we all are surrounded by so many different types of solids around us, but we see that all the solids they differ in the properties. The reason being the properties of the solids depend on the nature of constituent particles. Constituent particles means either atoms or molecules or ions. And these properties also depend upon the binding forces, that is the forces which are present between these particles. And based on these both, we get different arrangements of particles. And because of the different types of arrangements which arise because of different types of binding forces and the different types of particles, we get several types of structures. In general, if we see in the solid state, which we see around us, for example, if you take your book, chemistry book, it has a definite mass, the mass remains definite, it occupies a definite volume, and it has a definite shape. It is true for any solid. And this you have learned from your lower classes as well. In the class 5th and 6th, these are taught. The interatomic or intermolecular or interionic distance, as the case may be, they are short. The distances are short, means the distances between the particles are very less. Whereas the interatomic or molecular or ionic forces are strong. So what is less? The distances between the particles are less. Please take care students. The distances between the particles are very less. Means the gap between the particles is very less. There is no space. Intermolecular space, interionic space or interatomic space is very less. Whereas the forces between the particles, it may be interatomic or intermolecular or interionic, they are very strong. Since they are strong, the particles are held together tightly in their own place. They are tightly held together. Their constituent particles have fixed positions because of the strong intermolecular or interparticle force of attraction. They do not leave the positions. The particles have fixed positions and they can only oscillate about their mean positions. Only oscillation, to and fro motion is possible about their mean position. Since the interparticle space is very less, the gap between the particles, that is between atoms, ions or molecules, is very less, we cannot compress them further because they are already very close together. How to compress? Now in any bench, if already more than 2 students are sitting, we cannot ask them to accommodate one more student. It's not possible. There is no place left. Here also same thing. They are incompressible. That is why they are rigid. Now, based on the nature of order, that is whether there is orderliness in the arrangement of the constituent particles or not, we can classify the solids into amorphous and crystalline. Depends upon how much orderliness is there in the arrangement of the constituent particles. So first we say crystalline solid. In crystalline solid, there is a large number of small crystals present, and each one will have a definite characteristic geometrical shape. There is perfect orderliness in the definite arrangement of the particles. They are arranged in a particular pattern, and that pattern keeps on repeating throughout the whole solid. It has a definite characteristic geometrical shape. There is orderliness, and this orderliness is of a long range. It has a long range order. Now in my video, whatever I have written here, you can take this as notes also. So this will definitely help you. So students, please subscribe to my channel because I will be regularly uploading videos, and share the channel also. And we will solve the questions at the end, and also extra questions which will help you in your board exam. So please subscribe to the channel, students. So there is a definite characteristic geometrical shape to it. The arrangement of the constituent particles is totally ordered, as we will see. There is a regular pattern. You see in this diagram which I have drawn it ready for you all. You see there is a particular, you see this, if we see here two types of particles are there, that is, this is a general arrangement. So I am just using the word particles. So there is a regular pattern you can see. And this pattern in three-dimensional space, it will be repeating it periodically. Over this same pattern we will get along the entire crystal. And there is a property which we'll study here, that is called anisotropy. Crystalline solids except cubic crystals are anisotropic. Means some of the physical properties like electrical resistance or refractive index, they will show different values when we measure these values along different directions in the same crystal. If we change the axis of measurement, the values may differ. Then it is known as anisotropy. Why this arises? This arises because there will be different arrangements in different directions. Orderliness is there, that is perfect. But this orderliness is also different in different directions. As we can see here, you see in this diagram, there are two types of particles here. This is the arrangement. If you see along the AB axis, we get along the same axis, same type of particles are there on the right side and the left side, same. But if you see around CD plane, the two types of particles are alternating with each other. It is ordered, there is orderliness, same pattern you will get throughout the crystal, everything is correct. But if you see along the different directions, the arrangement of particles is not the same. That is why some of the properties which when measured along different axes, you will get different values, as I have just told here. Different values you will get when you measure along different directions in the same crystal. So here also see there is perfect arrangement, perfect ordered arrangement, and this arrangement will definitely repeat throughout the crystal. But along different axes, the arrangement of particles is different. Along AB it is different. Along CD it is something else. You can see it's very clear. That is why it leads to anisotropy. Whereas in case of amorphous solid, what we find, there is no orderly arrangement of particles. There is no orderliness. Even if there is some sort of orderliness, it will be present in a very short area. After that you will get something else. Means the arrangement of particles has a short range order and it does not repeat periodically. Means a regular periodically repeating pattern, it will be over a short distance, scattered here and there, and in between the ordered portions there is disorderliness. Means disorderliness is more. Within that somewhere you will get some orderliness over a short distance, short range. See, you can take the example of a classroom. In a classroom, let's say there are 25 chairs, 25 benches, okay? Among them, here and there you will find that there are 3 or 4 benches in which the students are sitting perfectly. The number of students are the same as per the rule. Means if it is two students should sit in a bench, it is like that. In 3 or 4 benches only here and there. In every other place, either the students are standing here and there or they are sitting in some other direction. Means there is perfect disorderliness. Then it is amorphous solid. Example will be quartz glass. You see here in this diagram, you see the number of particles in each ring is not the same. Here it is something, here it is something, here everywhere it is changing. There is no orderliness. Okay, we don't find any sort of orderliness. The arrangement is different. Now we will go through the properties of crystalline solid. The crystalline solids, they have a definite characteristic geometrical structure, as we have seen. They have a particular definite ordered geometrical structure. They melt at sharp and characteristic temperature. They have a sharp melting point because all the particles are at a same distance from same number of neighboring particles and same type of neighboring particles. So, same amount of energy will be needed to break every interaction. Whatever bond is present in the three-dimensional structure in every axis, for breaking every interaction we require same amount of energy because there is perfect orderliness. So they melt at a sharp and characteristic temperature. When they are cut with some sharp object, sharp edge tool, they split into two pieces. And every piece will have a plain and smooth surface. This is also again because of perfect orderliness. They have a definite and characteristic heat of fusion. They have a characteristic heat of fusion. Anisotropic in nature, I just explained, because the arrangement of particles is regular and ordered among all the directions, but along different directions, if you see, the arrangement of particles will be different along different axes. They are perfect true solids. The intermolecular forces are totally equal and they are true solids. They have a long range order. We have seen whatever orderliness is there, it will exist throughout the crystal. Orderliness exists throughout the crystal. They have a long range order. Now we come to properties of amorphous solids. See, amorphous solids, they have no regular structure. They do not have a regular structure. We have seen the arrangement is totally disordered. They gradually soften over a range of temperature. Okay, slowly they will soften because there is no orderliness. When they are cut with a sharp edge tool, they cut into pieces with irregular surfaces. The arrangement of particles is randomly disordered. So when they are cut, we get irregular surface. They have no definite heat of fusion. Heat of fusion is not definite again because the bond energy to break the bonds, that may differ because see, there is no orderliness. So they do not have a particular or definite heat of fusion. Whereas we have seen that the sharp melting point exists in crystalline solid because amount of energy which was required in crystalline solids to break every interaction was same. That was because of orderliness in crystalline solids. Here it is opposite. They are isotropic in nature, we have seen in the diagram. For anisotropy, I have drawn the diagram. Opposite will be for isotropic. That is, there is no such difference. Okay. They are pseudo-solids. They are pseudo-solids or supercooled liquids. Because see, if you see the glass panes of windows of old buildings, we find that they are thicker at the bottom. This we find in case of amorphous solids. They are supercooled liquids, means they tend to flow slowly from solid to liquid. So they are supercooled liquids, we can call. They have a short range order because arrangement of particles is randomly disordered. So they have a short range order. And particularly fifth point, isotropic in nature is very important. They exhibit uniform properties in all the directions. They exhibit uniform properties in all the directions. So I hope students, you all could understand the topic which I discussed today. Please subscribe to the channel and share this video among your friends. Thanks for watching. Please subscribe to the channel. Thank you all.